Isaac Newton said that as we move farther away from the region where most of the mass is concentrated, the velocity of the bodies in orbit must decrease. We expect this idea to extend to galaxies, except what we observe is a bit farther than what we expect, or should I say faster. The stars at the visible rim of the galaxy are moving so fast that we expect them to fly off because the mass we see is theoretically insufficient to keep them in orbit. Scientists think that there must be some invisible mass holding them together, and this invisible mass is much larger than what we see. We call this dark matter. If this mass is much greater than the luminous mass or regular stuff like dust, planets, and stars, then this can have a dominant effect on the trajectories of the particles around the central black hole of galaxies. To see how it works, let's construct a galaxy. We take a simple, non-rotating, and uncharged black hole and immerse it in a spherically symmetric dark matter distribution. We assume that the dark matter particles move around the black hole in perfectly circular and concentric orbits. Furthermore, we will use a Newtonian potential called the Hernquist potential to describe the distribution of dark matter. The Newtonian description of gravity breaks down at strong gravitational fields like near the event horizon of a black hole. However, we still want a Newtonian observer far from the black hole to agree with us and say, okay, we really have a black hole surrounded by a dark matter distribution following a Hernquist potential. We will use isotropic coordinates in our construction, and this just means that we treat the x, y, and z directions equally. In this thesis, we have shown that it is possible to get an exact space and description of our setup using isotropic coordinates. In our spacetime, increasing the compactness of the dark matter halo lowers the energy requirement for an incident massless particle to plunge into the black hole. This translates to an increase in the radius of the black hole shadow. Want to know more? See you at my thesis defense.